It's actually why left. Actually looks pretty safe.
Too bad we don't need to choose.
Okay, and once I was,
That's a good
however,
thing.
once I started doing my research on that,
Yeah. But like, you're the only teacher that would accept that cheating method.
Maybe.
Very bottom.
All right, let's take a look. Page 255, we're going to take a look at our last graphing example. Try to relate some properties that we might have identified or realized based off these graphs, and then try to extend those ideas to, well, what if we have a table? Okay, how can we still use these properties if we don't necessarily have a graph? And we might actually be able to start the next section today, but we'll see how far we get. So when we were looking at these graphs yesterday, we are either looking at the ends of the graph, like do we go forever to the left or forever to the right? Sometimes though we can take a look at what a graph is doing at a particular point. For instance, what's happening at -2 from the left and the right, what's happening at -3 from the left and the right. So we're going to see kind of what those characteristics have for this particular graph. Looking at the first one, can you describe what the graph is doing on the left-hand side? When we did polynomials, we normally said it rose or it fell, but for rational functions that might not be the case. What's this graph doing on the left? Approaching 2, okay? What's this graph doing on the right? See, it's also approaching 2? Okay. Now, the left-hand side is approaching 2 from the top of a horizontal asymptote. On the right-hand side, it's approaching 2 from the bottom of an asymptote. But either way, you're still approaching 2, just from larger values or smaller values. What if we take a look at -2? So here's the x value of -2. We're going to trace the left-hand side. Notice how we're getting closer and closer to the hole. So what's the y value that we're getting closer and closer to? -1, right? The height of the hole. If we trace the right-hand side, we're still getting closer and closer to the hole again. So that would be -1. Let's try -3 this time. All right, there's -3. If we trace the left-hand side, the graph goes up forever, so that would be positive infinity. And if we trace from the right-hand side, the graph would go down forever, so negative infinity. Coming back a little bit. Okay. Let's try domain. So as we drag our pencil left and right, let's see if we got to skip over anything. We have an arrow to the left, negative infinity. As we drag our pencil, we eventually get to the vertical asymptote. So we got to skip over that. That happens at -3. As we continue to drag, we get to -2, which has a hole. So we'll have to skip over that spot as well. And after the x value of -2, we really don't have any other vertical asymptotes or holes. So we're good to go to the end. Positive infinity. For range, we're going to do the same thing, but drag our pencil low to high. So the lowest, we have an arrow going down, would be negative infinity. As we drag our pencil up, we encounter the hole, which has a y value of -1. So we'll skip over that. As we continue to drag, we reach a horizontal asymptote, and that y value is 2. So we'll skip over that. And after that, we're kind of home free because there's no more holes or horizontal asymptotes. So we'll go towards infinity. All right, so keeping these different characteristics in mind, whether we want to look at the ends of the graph or the particular point on a graph or location on a graph, maybe domain and range, let's see if we can make some generalizations, if I can talk today. All right, so on the next page, let's kind of think about this mathematical notation and what it's telling us based off of a rational graph. If the graph of y values are approaching a number, we're just going to let that be letter A. So if we know a graph is approaching a y value of a specific number, as the x values become increasingly larger or increasingly smaller, can we think about what characteristic the graph might have? If the y value approaches a number, but the x values get increasingly larger or increasingly smaller. Well, that'd be the other way for you. Larger this way, smaller this way. Yeah? Horizontal asymptote. Okay, the y value is leveling off as you go to the left or the right. So we'll write horizontal asymptote. Let's think about 2. What if the y value is approaching a number, but this time the x value is also approaching a number? So instead of going to the ends, you're now approaching a particular spot from the left and the right, yeah? It's going to be a hole. Because at a hole, the left and the right have to meet, so the y value would be the same number. And then for 3, what if the y value goes up forever or down forever as the x value is approaching a number? So as you come into a particular spot from the left and the right, okay, the heights go up or down forever. Can we visually think about that? As you come in from the left and the right to a particular spot, you start to drastically change. What does that kind of look like? A vertical asymptote. Okay, so if we can identify these characteristics based off of a graph that have these particular properties, maybe we can use these properties in a table format to see if we can figure out where's a horizontal asymptote, where's a hole, where's a vertical asymptote. Okay, so we'll take a look at a table example in a second. We also discussed, though, maybe some patterns with the domain and the range. So when you think about identifying all the numbers that you can plug into a function, meaning domain, and all the numbers that you could get out of a function, meaning range, can we find a pattern to help us immediately determine what those values might be? How can you find the domain of a rational function? Can we generalize it? Yeah. Okay, x values. So find x values of holes. And what was the other one you said? And vertical asymptotes. And what are you going to do with those x values once you find them? How can we use those numbers to help us write the domain? Can we go back? So on this graph that we did, we saw that there was a hole at -3, or sorry, a vertical asymptote at -3, a hole at -2. Somehow those showed up in the domain. What did we do with -3 and -2 when we wrote the domain? Yeah? You stopped or you skipped over them. Okay, so find x values and skip them, okay, in the domain. Can we maybe think about how that statement might be related to the range? How can we find the range of a rational function? You my idea, Travis? Yeah.
Yeah, you'd find the points, the holes, the y values of the hole
Okay, so find y values of holes
and
and horizontal asymptotes this time. And skip them in the range. Okay, so for both of these, we're going from negative infinity to positive infinity, but we're skipping over particular undefined locations, either undefined x values, like holes and vertical asymptotes, or undefined y values, meaning holes and horizontal asymptotes. Because if you have a hole, it's technically an ordered pair, where you're going to have an x value and a y value. That's why we're counting it twice. Okay, just x for the domain, y for the range. So keeping these 5 generalizations or patterns in mind, let's see if we can maybe do something similar in a table format. So not a graph anymore, we just have particular values to look over. So they tell us that this is a rational function. We know it kind of has that curvy shape to it with some asymptotes, maybe holes. So based off these numbers, let's see how far we can go here. Identify the equation of any horizontal asymptote of the graph. Do you think we level off at a particular spot to the left and the right? Or do we rise and fall like a polynomial does? What do you think based off the table? Can we think about if you were to go very, very far to the right on this table, does it look like the graph would go up forever, down forever, or does it level? What are the numbers telling you? What do you think? It's leveling, okay? Notice how very, very far to the right, okay, like 500, all the way down on the x-axis, our y value is 1.5. And when we were only at 2.1, okay, there's a big jump in the x values, right? There's a very, very small jump between the y's. So you're not really going up forever or down forever because you're only growing this much. Okay, you're only growing a very, very small amount. So you must have that leveling happening. If you have a really big change in the x's, but a small change in the y's, notice how to go that span with only that height, you'd have to be practically level. We kind of have the same thing happening on the other side, okay? Notice how very, very negative numbers with seems like we're approaching a particular height. So we'll go ahead and say horizontal asymptote at the y value of 1.5. It says give a reason for your answer. So because I don't know, the extreme left and right are close to 1.5. So this is very similar, maybe we'll write this down, very similar to end behavior for horizontal asymptotes. Polynomials, we only had 2 options. We either rose or we fell. But for these rational graphs, we do have a third option, and that's this leveling idea of a horizontal asymptote. Does that make sense? I hope. Okay. Let's see. Based off the table, can we find the location of a vertical asymptote? You ready, Travis? Yeah. Why here? Uh-huh. Okay, so it's an undefined location, which means it's either a hole or a vertical asymptote, so something's definitely going on at 2. And how did you know this was a vertical asymptote instead of a hole?
Because the numbers get like really small right on the side of it. I mean, that could be wrong. Not gonna lie.
No, it is. It is a vertical asymptote. You said, so what's happening with the numbers around it? You started to mention something with that.
Yeah. Oh, I didn't even look at the y value.
Oh, so the x values are really close, right?
Yeah.
So that's good too. Notice how on the left-hand side, you're very, very close to the horizontal asymptote, but you have a very negative y value, so you're very below the x-axis. And then on the other side, which is also really close to 0.5, you have a very positive y value, meaning you're very above the y-axis. So at this one spot, you're undefined, but on the left, you're very low. The right, you're very high. Okay, so we kind of have that divide happening where they're drastically going in different directions. One's very low, one's very high. So visually, if we think about it, it kind of makes sense that that would be a vertical asymptote location. So we'll say here, because the y values around this spot are drastically different. Okay, one's very negative, one's very positive. So you have that kind of drastic movement in the graph where you're going in opposite directions. Now if we take a look at the spot of 2 and look at the numbers around there, do you notice how that pattern is not really happening here? We don't have that drastic difference between the points. Okay, actually these are not drastically different at all. Aren't they extremely close? So what do you think is happening at 2? If you have an undefined spot, but the points on either side are extremely close together in height, what does that kind of look like? We thinking a hole? Okay, so we'll say hole at x equals 2 because the y values around this spot are extremely close together. Can we think about maybe what the coordinate of the hole would be? We know the x value is 2 because that's an undefined location, but can we think about what is the height of that open circle if we had a graph? If we're 1.604 on the left and 1.596 on the right, what does it seem like we're really close to? 1.6? I think that'd be a good educated guess. Okay, probably realistically you could pick anything between those values because we don't really know, but I'd say 1.6 is a good guess. Okay, so notice how without a graph, just some table of numbers here, we can identify some certain characteristics, and I think we have enough information to help us write the domain and the range of this rational function. Okay, maybe go back to 4 and 5 with our little patterns that we noticed to help us write these pieces. So for domain, we said we have to skip over the x values of any holes or vertical asymptotes. And in our questions here, we identified a vertical asymptote at -0.5 and a hole at 2. So in order, we're going to skip over those two x values. We'll do -infinity to -0.5, -0.5 to 2, and then 2 to infinity. For the range, we said we had to skip over the y value of the hole and a horizontal asymptote if we have one. So we said horizontal asymptote was at 1.5 and the y value from the hole is 1.6. Okay, they're pretty close together, but we still are able to skip over those. So in order, the 1.5 would come first. So we'll skip over that. And then next we'll skip over the 1.6. We don't have an equation, we don't have a graph. All we have is a table of some information, but yet we're still able to pick apart and identify certain characteristics that this graph might have. We doing okay? I hope. Okay, good. So that's it for this section. We're going to take a look, though, a little bit more in the next section on how the graph and the equation are related We did a little bit of this yesterday, but this section's just going to hopefully let it sink in a little bit for us. So on page 259, we have 4 graphs listed on the front, and they also give us the equations of the graphs, and if there is a hole, they give us the coordinate of it. We're not necessarily going to write anything on this page, but we are going to have to keep it handy to reference because we're going to have to flip some pages. So on the back of this page, we're going to try to fill out a similar chart to one that we did in a previous section, but taking a look at some other characteristics. So we might have to flip back and forth between the graphs and this chart as we go through some of these columns. All right, so for our first one, let's see, we're going to rewrite the function in completely factored form. I think the bottom is going to be pretty simple for us. It's an I am setup. 2 numbers that multiply to -6 but add to -1. Can we think of those values? Yeah. -3, +2. Okay. The top, on the other hand, does not fit that I am method. It has an A value of 2. So we're probably going to have to go through this A times C process. So A times C would be -6, B -5. Can we think of 2 numbers that multiply to -6 but add to -5? Yeah? -6, +1. Okay, so from here you have options. You can do grouping or divide and slide, whatever your preference is. I'm going to do divide and slide. Okay, x minus 6, x plus 1. Divide by the A value of 2. 6 over 2 can simplify to 3. 1 over 2 does not simplify, so we can slide the 2 in front of the x. Now, based off of those factors, can we find some restricted values? Can we find a location of either a hole or a vertical asymptote? Just an undefined location in general? Can we find a number or 2 that wouldn't work in that fraction? Good, Lizzie? 3, -2, good. Numbers that make the bottom 0. All right, now that it's factored, maybe we can simplify it a little bit. Do you notice anything interesting with the factors that we have? If we're dividing? You see it, Blair? Yeah. Okay, so the x minus 3's would cancel. So we're left with a simplified form of 2x plus 1, x plus 2. And you even went on to say that 3 was a whole. So that's actually leading us into our next column here. So 3 was a whole because the factors canceled. You'd have a 0 over 0 if you plugged in 3. Can we classify this -2 restricted value as anything? If -2 would make the bottom 0 but not the top? Yeah? That's your vertical asymptote. Good. All right. What factor cancels out of the function and what type of discontinuity occurs here? Okay, we kind of already mentioned this. So the factor that canceled was the x minus 3. And we notice how if it canceled, it produced a whole. In the last column, what factor does not cancel from the denominator? That was x plus 2, and we said it was a vertical asymptote. So let's see if our analysis based off the function, okay, based off the equation, actually matches the graph that they gave us. So I'm going to flip the page. F of x is this first graph. Notice how, based off the picture, we have a vertical asymptote at -2 and a hole at +3 if we're just looking at x values. So it seems to check out. Okay, those are the numbers that we identified based off the equation itself. All right, let's try the next one. We're going to factor top and bottom. Both of these are I think we can do these. X plus 3, x plus 1, x plus 3, x minus 1. Restricted values, numbers that don't work. You got it, Olivia? 1 and -3. Okay. Can we, so we know something's going on here, either a hole or vertical asymptote. These numbers don't work, meaning it's an undefined location. Maybe we'll get a little bit more specific in a moment. Can we simplify this fraction? Yeah, what do you notice, Olivia? There we go. So we're left with x plus 1 up top, x minus 1 on the bottom. So if the factor of x plus 3 cancels out, we must have a hole related to that factor. So that would be -3 that we identified from our restricted value. X minus 1 did not factor, or cancel rather, from the bottom. So that's going to give us a vertical asymptote. The related x value to that factor is 1. Let's check it out. Graphically, if we flip the page, g of x, thank you. Okay. G of x is the second one at the top. We have a vertical asymptote at 1 and a hole at -3, just like we said based off the equation. Can you guys try the last two? Without looking at the graph, try to figure out where's there a hole, where's there a vertical asymptote. What's that?
Who does? This guy. Idiot. I know. -2 and -3. Robert, do you do that? Probably does. Probably does. You can do I am on the line. You can do I am on the phone. I know you have to do it. You are in this edition. You have to do I was. want to get through it. I'll just see for the third time. Let's see if we can see it for a third time. Yeah. Is that all we're doing for today? I signed up for the poster. What poster? The poster of the movie.
Alright, looks like we're good to go. Let's check these out. Livia, can you factor the first one for us? Okay, and for the top, stays an x plus 2. Looks good. Caitlin, can you find our restricted values? -3, -2. Good. Numbers that make the bottom 0. Maggie, can you find our simplified fraction? 1 over x plus 3. Okay, so notice how we have an x plus 2 factor up top, and in the bottom, those can go away. Matt, can you find a whole or vertical asymptote for us? Just do one.
2 or -2 is the whole.
Because?
Because it cancels out on both the top and bottom.
Okay, so the factor would have been the x plus 2 that canceled, and that creates a whole at its respective x location. All right, and Alicia, can you find a different characteristic? All right, because the factor x plus 3 is left in the bottom. It did not cancel. How did we do with that one? Good? All right, Logan's not here. Erica, can you factor the next one for us? I like it. Okay. Jack, can you find restricted values for us? -3, -2. Good. Numbers that make the bottom 0. River, can you do a simplified fraction?
2x plus 3 over x plus 3.
What canceled?
The x plus 2.
X plus 2's. Alright. Grace, can you find a whole or vertical asymptote for us?
X plus 3 or -3 would be
Okay. -3 vertical asymptote because the x plus 3 factor is left on the bottom. Okay, did not cancel. And then Blair, can you find anything else for us?
-2 is a whole because
The x plus 2 factor canceled. Good to go? Perfect. Okay, we'll stop there for today. We're going to take a look at some more graphs and generalizations and properties, relationships, all that jazz on Tuesday. We realize we're off Monday, right? Or at least you are. You are.
I am.